There's an old saying that you are the average of the people you spend the most time with. Believe it or not, that is basically an entire machine learning algorithm dressed up as folk wisdom. It's called k-nearest neighbors, and it's one of the simplest ideas in the whole field. So simple it almost feels like cheating. The intuition is that similar things tend to sit near each other. So to make a prediction about something new, you don't build a model, you just look at what's already around it. Let's unpack exactly how that works and where it quietly breaks down. Now, to appreciate how unusual this method is compared to almost every other model you've met. Most algorithms train an equation. They chew through your data up front, fit a set of parameters, and then throw the raw examples away. Prediction afterward is fast because all the learning is already baked into the numbers they found. The heavy lifting happens once before you ever ask a question. This method flips that on its head. There's essentially no training at all. It just stores every labeled example you give it, exactly as it arrived. All the real work happens later, at prediction time, when a brand new point walks in and asks who its neighbors are. The learning is postponed until the very last moment. So how does it actually classify a new point? It's a short, honest little routine. Store everything. Every labeled example you have is simply kept in memory, exactly as it came in, untouched. No model gets fit. No weights get learned. Nothing gets summarized. That's precisely why people call it a lazy, instance-based method, because it puts off all the effort until you actually need an answer. Measure the distance. When a new point arrives, the algorithm computes how far it sits from each stored example, usually with plain Euclidean distance, the straight line kind you learned in school. Close means similar, far means different, and that's the whole notion of similarity here, nothing more mysterious than that. Keep the closest ones. Out of all those distances, you hold on to just the k-nearest neighbors and ignore the rest of the data set. That number k is the one knob you really tune. Take a vote. Among those k-neighbors, the most common label simply wins and becomes the prediction. For regression, you average their values instead of counting labels. Simple as that. No equation in sight. No parameters to fit. Just the crowd nearby speaking up. All right, 3 things are worth burning into memory about this algorithm. First, it is lazy and instance-based. There is no training phase, just stored examples, which makes it wonderfully easy to understand and makes no assumptions about the shape of your data. Second, prediction is a majority vote of the k-nearest points. The choice of k really matters here. A tiny k chases noise into jagged, unstable boundaries, while a large k oversmooths everything and can wash out the real local structure you actually cared about finding. Third, the costs are real. Every single prediction compares against the whole dataset, so it's slow and memory-heavy at scale. It needs feature scaling, so no one feature dominates the distance, and it degrades badly in very high dimensions, where the curse of dimensionality makes everything look equally far away. Let's gather the essentials before we wrap up. This algorithm classifies a new point by a majority vote of its k closest store examples. It is lazy and instance-based. There's no real training. It simply remembers the data and compares distances at prediction time. The value of k trades noise against smoothing, and features must be scaled so no single one dominates the distance. Slow at scale and shaky in high dimensions, but a fantastic baseline and the intuition behind modern vector search. Want more of these plain-spoken ML breakdowns? They live at standarity.com. Swing by any time.